Well, I want to thank you all for having me. It's fun to be in sunny California for a couple of days and freezing. Yeah, right. So Marta asked me to talk about low-mass black holes, which means that I'm mostly talking about hard work that other people have done and have kindly allowed me to collaborate with them, particularly Amy Rines, who's an Einstein Fellow who will be here next week in the conference, so you'll hear much more about her work next week, and also Brendan Miller, who's been working with Elena. Okay, so long ago when I started my PhD thesis, a really pretty nice story had emerged in which supermassive black holes were strongly associated with the bulges of galaxies. And this came about from two types of observations. First is shown here. This is just saying that we find active galaxies in massive bulge-dominated galaxies, not in late-type bulgeless galaxies, and basically almost all massive bulge-dominated galaxies, so sometimes sort of accretion if you look hard enough. So that was type of evidence 1. Type of evidence 2 were these strong scaling relations between black hole mass and bulge properties, velocity dispersion shown here. But of course, it's really hard to find little tiny black holes in galaxies that are forming stars, and so there are severe selection effects which make it basically difficult, if not impossible, to pin down how often supermassive black holes are found in late-type spirals. Likewise, I think Remco told you that there is a lot of bias against spiral-type galaxies in terms of dynamical black hole masses. So our understanding of the demographics of low-mass black holes was really incomplete. And I want to address two separate but both interesting questions here. So first of all, what are the lowest mass black holes in the universe? And what does that tell us about seed formation mechanisms, which I think you talked about in detail last week? And then the other question is whether we can actually tie the growth of bulges to the growth of black holes in any compelling way. So this is just a beautiful figure that Marta made showing the different ways theorists have come up with to make the first seed black holes at high redshift. So you can make them the way we know we make black holes today from the collapse of massive stars. Early on, these stars would have been very massive, so you could make 100 solar mass seeds. Or you could do something magical and get low angular momentum gas to somehow form a big black hole right away, a 10 to the 4 solar mass seed. Or you could have some runaway dynamics in the center of dense star clusters. And in principle, each of these different seed mechanisms imprints itself into the occupation fraction of black holes in low-mass galaxies today. In particular, in a cartoon sense, if you do some sort of direct collapse, fewer low-mass galaxies today will have black holes, but those black holes will be larger. So the assumption is that the black holes in these small galaxies don't grow very much. If you use POP3 stars, all the galaxies will be seeded, but they'll be seeded with really little black holes, 10 to the 3 solar mass black holes. So we would like to know how often little galaxies contain black holes. We'd also like to know whether there are any scalings between the black hole and the galaxy at this low mass regime. I won't really talk about this today too much, but in principle that could tell us more about seeding mechanisms. Unfortunately, while there's all of these rich things that we could learn if we understood the population of low-mass black holes, we're still kind of stuck in the phase of trying to find them. So I'm going to give you a litany of different ways that people have used to try and understand where these small black holes live and where they don't. You've probably heard from Remco and others that the best way to find supermassive black holes is dynamically. So we love to measure the mass of the black hole based on its gravitational influence on stars in its vicinity. But little black holes have very small gravitational spheres of influence, which means that you cannot weigh them very much outside the local group. And this slide, I think, has almost all dynamical black hole mass measurements that have been made for low mass galaxies. So M33 was the classic one, came out right around the time of the M sigma relation, and people said, look, this is a galaxy with no bulge. Black holes are uniquely associated with bulges. If you don't have a bulge, you don't have a black hole. Since then, there's been some controversial detections of 10 to the 4 solar mass black holes in these very massive globular clusters, which may be globular clusters or may be stripped galaxies. And Neil Seth has a tentative detection of a 10 to the 5 solar mass black hole in this really small S0 and GC404. And there are some limits now on the presence of black holes, or upper limits on black holes in these dwarf elliptical, local dwarf ellipticals. And that's about it. Another way we could measure black hole masses is through using the gas as a dynamical tracer with reverberation mapping. There are, I guess now, 2 attempts to do this with black holes below 10 to the 6 solar masses. One was Peterson et al. 2005 for NGC 4395, our poster child that I'll introduce you to in a minute, and more recent work by Rafter and Caspi and collaborators looking at one of the objects from my thesis sample and maybe getting a black hole mass of a few 10 to the 5. Apart from that, we're pretty well stuck just using accretion as an indicator of the presence of a black hole. So now we're at the mercy of whether or not a little bit of gas gets to the black hole, but at least this will allow us to show that there are indeed black holes in galaxies without bulges. So most of the work probably still has been done in the optical, either looking at the line ratios and saying, okay, you need a hard ionizing spectrum to produce the line ratios that you observe, or we see very broad emission lines like Mike talked about yesterday. There's even some work at higher redshift now, led by Jonathan Trump and Stephanie Juneau, apparently finding accreting black holes in sort of 10 to the 9 solar mass galaxies at redshift of 1. In principle, we should do better if we get away from the optical, where we're biased by star formation and dust and optical selection, and focus on the X-ray and, in principle, also the radio. I'll talk in a little bit more detail about work that Elena is doing, but in general, these samples are quite small still. Nothing systematic has been done for large volumes yet. And there's a little bit of work with mid-infrared spectroscopy, same game as the optical line emission, this mostly led by Shobita Satyapal, and just now starting to use tidal disruption. So in principle, if there's a massive black hole there, every once in a while, a star will wander too close and get eaten. If we have high cadence photometry or radio photometry, we should be able to catch these things and then, with enough monitoring, back out an occupation fraction that way. So I'm looking forward to this field growing in the near future. So this is basically everything people have done. And let me just highlight some of my favorite objects now. So this is our poster child. This is NGC 4395. This is 4 megaparsecs away. It's a bulgeless galaxy. It doesn't look like an AGN host galaxy at all, but it has this beautiful optical spectrum, which shows very high ionization lines, indicative of a hard ionizing spectrum from an AGN. Also broad Balmer lines, again, telling us that there's gas moving in a deep potential. It also has a compact jet. It's very variable in the X-rays, and it's pretty well established that there is a 10 to the 5-ish solar mass black hole at the center of this galaxy. It's sort of twin POX52, which is Aaron Barth's rediscovery, very similar spectrum. So both of these served as a proof of concept that indeed in these Smurfy galaxies you can sometimes host supermassive black holes. So M33 tells us that not all low mass bulgeless galaxies contain black holes. 4395 tells us that some do, and we still would like to determine what that fraction is. So, oops, sorry. Well, that's a mess. Sorry, I'm going to fix that. I want you to be able to see the slide. Okay. So this is just what I did for my thesis, which was to go through Sloan and use the optical spectra to select a black hole mass selected sample. That is to say, use the luminosities and the line widths to pick black holes we thought were low mass of around 10 to the 6. And we were finding host galaxies about a magnitude below L star. So small galaxies, but not really that small. And this is a complementary sample that Aaron Barth selected that are obscured systems just picked out by narrow lines. So can we get into the real dwarf regime, like LMC-type galaxies? And this is where Amy's work comes in. Oops, first I'm going to tell you about Malte Schramm's work. There are now a lot of deep X-ray surveys, in particular this 4 megasecond Chandra Deep Field South pointing, where we have not only depth but also temporal information. And we can start playing what is really a pretty dangerous game, which is, okay, let's take the galaxies with low masses, so LMC type stellar mass and below, a few 10 to the 9 and less. And let's look at all of the ones that have X-rays. And then let's pick the ones that have, we think, too many X-rays to be explained just by their star formation.
So these are objects in which the optical line is not dominated by the accretion disk?
Absolutely not dominated by the accretion disk. Well, so we say there may be a broad line in one of them, but yes, they're basically type 2s. Even in my thesis sample, which are type 1s, the optical light's dominated by the host galaxy by a lot.
But you can do that because they're so close.
Well, they're at redshift 0.1.
Oh, so you don't, sorry.
Yeah. I mean, it's obviously aperture dependent. If I had a small enough aperture, it would be, but there's
no bright point light nuclear source in the output.
In my thesis objects, yes, there is. Yes, it's just that the contrast is low. So it's about 20% of the light in a sort of Sloan type aperture. So these guys were just selected to lie more than 3 sigma above the nominal sort of Lx over Lb relationship. They're not ironclad low mass black holes. They could be ULXs. This guy, which lies closest to the nominal relationship, is highly variable, and so seems like a much better candidate than the other two. The point just is that we made a cut in redshift so that we could have H alpha. There are a whole bunch of objects at sort of redshift of a half that we haven't looked at yet. But hopefully, looking more broadly in the Chandra archive, we can start to get a better census of the X-ray population in these low-mass galaxies, and at least statistically address how many of them are likely to be 10 to the 4, 10 to the 5 solar mass black holes as opposed to ULXs. Okay, so now Amy's work. You've probably all heard about this dwarf starburst galaxy, Henize 210. I have to tell you, I would never have looked for a black hole in this galaxy. It is starbursting all over the place. You don't know what the center is, okay? And when I first heard about it, it was actually from Ryan Hickox, and I said, forget it, there's no black hole. But, you know, the thing is, there are these big nuclear star clusters, which is what Amy was studying for her thesis, and there's a radio source and an X-ray source coincident, but not coincident with any of those superstar clusters, sitting off by itself in what we think is the dynamical center of this galaxy. So Amy has, I think, made the strongest possible case that she can, that there's an accreting black hole in the center of this galaxy. We don't know the black hole mass. She makes some guess of 10 to the 6 based on the fundamental plane. But she's now gone back with VLBI, and indeed there is a very compact radio source there. We also have a bunch of epochs of X-ray monitoring, which we're analyzing now. So inspired by this galaxy, Amy then went back to Sloan and said, okay, instead of doing what Jenny did for her thesis, which is to select things based on their AGN properties, I'm going to start with all of the dwarf galaxies in Sloan, particularly everything with the mass of the LMC and less. And she used this catalog put together by Mike Blanton and Marla Jiha called the NSA catalog, where they've taken redshifts not just from Sloan, but also from Arecibo. So it's trying to be as complete as possible within a volume of something like 0.05. And so she took 25 1,000 dwarf galaxies with emission lines, fit all of their stellar continuum to get really good measurements of their line ratios, and then selected everything with optical line emissions suggestive of an accreting black hole. So that's these 136 that lie either in Seifert land or in this sort of uncertain composite land. And of course, we're dominated by these. So who knows? Are they extreme star formers or AGN? It's unclear yet. And then a handful, 25 total, with broad emission lines, some of which lie in the standard Seifert land, and many of which lie here in star-forming land. So either there's a lot of star formation in the fiber, but we have a real AGN, or in some cases, pretty clearly, we have a supernova. So this is our main contaminant. This is just an example that we're pretty sure is a supernova. We got to get second and third epochs for all of these. Hopefully the supernovae will fade, but the AGN will stay, and we'll be able to cleanly separate them. But here's an example of a nice candidate. Supernovae are just one example of the sorts of stellar processes that start to really contaminate our sample when we're down right at the hairy edge where the luminosities are just low enough, the line widths are just low enough, and really a couple really exotic stars could start to really look like an AGN. So we're.
Did you pick that one out as a super? What makes you say that it's a super?
This is just one of the ones that has an asymmetric, very broad line, lies in the star-forming part of the diagram, and thus makes us very nervous. So we've got a third, I guess, a second epoch for all of them, in some cases 3. They're in our paper, which will appear on AstroPH on Monday, I think, in time for Amy's talk. But they make us nervous. There are a bunch with P Cygni profiles, so there it's easy to throw them away. And then there are these type 2Ns where they look like AGN.
You only see it in H alpha, the broad base. Is that true?
That is not always true. I mean, there are plenty of cases where we see whopping H beta and a P Cygni profile in H beta. Those are the ones that we've thrown away. So,
right,
yeah, in this case, that's true. That's true in this case. Here we see broad H beta.
You believe the top one, right? Is that what you're saying?
I think the top one is a very good candidate for being an AGN. What we really want is X-ray and radio data. It would start to give you a real warm and fuzzy feeling that you're finding real AGN. So with my thesis sample, they were much more luminous. They're all sort of 10 to the 40 to 10 to the 42 in X-rays, and there's just no real ambiguity that they're AGN, but they're also not in such excitingly small host galaxies.
Can I ask about the radio source that you were thinking would be a signature of an AGN? So what would you expect a core at the X-ray source?
Well, we don't have X-ray or radio for any of these, not uniformly.
As a discriminator, and I'm just wondering because if it doesn't have a radio jet, it's not radio loud, how would you distinguish it being an AGN?
Well, the ratio of X-ray to radio would be discriminatory. So at a certain point, you have the luminosity of the source. You have, sorry, Julian, am I saying something dumb?
No, I'm trying to listen to what you're saying. So yeah. So please speak.
Oh, okay. So there's certain ratios of X-ray to radio that you can get from a supernova remnant, that you can, and so we can start to rule out various stellar processes by getting both luminosities and ratios in these different bands. That's the goal.
Okay, but it's not a complete discriminator, mainly because you can have supernovae and whatnot giving X-ray radio as well. That's just where I was wondering.
That's right, but in principle, the radio spectral indices plus the ratio of radio to X-ray plus the optical diagnostics should start to put us into a corner. Whether it will be completely definitive in all cases, I doubt it, but I think if you could do this systematically, you would start to get statistically a feel for whether you were finding accreting black holes. So just a little bit more statistics on her sample. So again, this is This is the mass distribution of the parent sample here in black. Everybody's just renormalized. And this is the stellar mass for the host galaxy distribution for the entire sample and the ones that are nice Seyferts. Okay, so these are a little bit more massive than the full parent sample. If you take standard line width relationships for the broad line things, we're getting black hole masses of around 10 to the 5. And the absolute magnitudes are just quite a lot lower than what we were finding in my thesis sample. So she's really succeeding in finding accreting black holes in real bona fide dwarf galaxies. It's about 0.5% of the entire parent sample that show any signs of an accreting black hole in the optical. The problem that we continue to wrestle with, which I'll get back to at the end of my talk, is really, it's very nice to make these catalogs. It's nice to find these things, but ultimately we want to know the space densities and we want to know the occupation fraction. But in Sloan, because you're targeting things based on the optical luminosity of the galaxy, the AGN is too faint. You have these horrible selection effects to try and figure out which galaxies contain black holes. You're always targeting the most luminous galaxies. So ultimately, we're going to have to work a lot harder to turn these catalogs into something like an occupation fraction. All right, so now I want to spend a little bit of time on this question of whether there's a relationship, a fundamental relationship between black holes and bulges in particular, coming back to the scaling relations, and I want to show you my favorite version. So this is the M sigma relation as defined by red galaxies, bulge-dominated galaxies. This one happens to be from Gultekin. You get the same thing from McConnell. And then I'm showing in points all of our megamaser disk galaxies. So these are basically the most precise black hole masses outside of the Sagittarius A star. And we get them from the Keplerian rotation curves of these megamaser disks on sub-parsec scales. And what I think they're telling us is that there's basically no correlation between black hole mass and velocity dispersion in these disky galaxies. These aren't even small disk galaxies, okay? These are sort of L-star disk galaxies. But they don't really have classical bulges. So if you start to look in detail, I'll show you this now and get back to it in a second. At the centers, okay, we see star formation, we see disks. The life of the centers of these galaxies is still dynamic and gas-rich. And so, what I think this is saying is that there is something important about making a bulge that also establishes these scaling relationships between black holes and bulges.
Sorry, what is sigma star?
So sigma star is measured for the bulge-like part of the galaxy.
No, you said there's no bulge.
I said the bulge is not a classical one.
Oh,
but if I
Okay, you take whatever is the closest. Okay.
So if I just plot the light profile, this is surface brightness versus radius.
Yeah.
There's something that's like a disk. It's an exponential. And then there's a whole bunch of other stuff.
Okay.
And the velocity dispersion is measured for that.
Okay.
Now, if you want to look at the radial profile of that velocity dispersion for just these stars, it's probably going to look like this. A lot of them have sigma drops. So because there's young stars in here and they're forming in a disk, and so sigma gets low. And so sigma itself probably doesn't mean a whole lot taken alone. We can also plot bulge mass. We're not going to find a different answer. I think basically the black holes are small compared to the mass scale of the galaxy, no matter what you plot on the x-axis.
Do they have nucleus, the clusters?
They're just not quite close enough by to answer that question. Say it again? Yeah, so Circinus is close enough. And probably they do, just statistically speaking, but we cannot study them for the majority of these. They're typically at 50 megaparsecs.
4258, of course, is a wonderful example because the kinematics are so clean. The disk is very...
In the maser. Yeah.
I was noticing no vertical error bars in that plot.
No, they're there.
Oh, really?
Oh, yeah. Oh, yeah. So the error bars currently, there are currently 10% error bars, and that's dominated by the distance.
Well, I guess, for example, in 1068.
1068 and Circinus have bigger error bars.
Right, and in the initial report some years back, the velocity profile was particularly not Keplerian.
That's right. That is not the case for the rest of the points on this plot.
Okay,
They're beautifully Keplerian.
Okay, and equally quiet.
By quiet. There's nothing that looks like an outflow in any of these. They're all being sort of pruned for distance measurements.
Yeah, what I mean is scatter around that mean or minus that.
Yeah, it's basically consistent with measurement. And so the other beautiful thing that's in Chang Yu's paper is sort of ask what's the deviation from Keplerian, and then could this be anything other than a black hole? And for almost all of them, you can say not. I mean, astrophysically plausible alternatives.
Okay.
So, sorry, I didn't actually bring my plot of all the rotation curves, but they're not as clean because they're further away. They're also, the amplitude is not as high, it turns out, as 4258. So 4258 is still the cleanest in that sense, but they're all very, very clean. So we also wanted to address this question of whether black hole mass correlates better with dark halo mass. There are lots of theoretical reasons why we would like that. If halo mass determines galaxy life history. And you could also imagine that if feedback is what sets black hole scaling relations, that feedback could also happen on the halo scale. Or potentially feedback is irrelevant, and instead what sets black hole scaling relations is just hierarchical merging. Okay, so the mass function has an exponential fall off. There's lots and lots of merging at low redshift, and this by central limit theorem leads you to a tight relationship between stellar mass and black hole mass for high mass galaxies. This was first suggested by Chen Peng and then elaborated by Knud Janke. In this case, you would expect halo mass would be the driving parameter for black hole mass rather than bulge. Yeah.
To have that, you really need a very large number of black hole mergers. Seems really on the high side of what anyone would have. To get to the central limit theorem, you need very frequent mergers. So pretty much all galaxies in the universe have black holes in the mergers.
And this is to explain the scatter, or just to get a relationship at all?
Just to obtain a tight relationship.
A tight relationship.
To obtain a relationship at the high mass level. Well, probably at least 10 mergers per galaxy.
Is that too high? I mean, you know better than I do. Okay. See, I like this picture, but I'm not wedded to it. Anyway, so my graduate student, Ailey Sun, got H1 rotation curves for a bunch of the megamaser disk galaxies, and this is not a pretty figure, but this is what it looks like. So black hole mass versus circular velocity. These are her measurements. The punchline is that there's a lot of scatter, and she did her best to separate intrinsic scatter from measurement scatter, which is hard. And if you just take a matched sample, well, there's Remco's black hole for reference, although maybe its mass has changed by now. I don't know. Oh, sorry. So this is the clean version now. So this is still circular velocity versus black hole mass, and the matched version for sigma. And basically, if you take the same exact galaxies for both relationships, we're getting comparable scatter between the two. Okay. And so our interpretation, which I'm sure is overly interpreted, is that merging alone doesn't get you there, because the halo doesn't seem to be special compared to baryonic things like sigma star. In any case, that's the observation. We're really, really limited by the fact that it's hard to get rotation curves for these massive galaxies. So perhaps we should start using dynamical models. That'll give you a measurement of the dark halo. We were scared to do that here because that's not what we're measuring down here. But without that leverage, we really can't constrain the slope and the scatter. So that's where we are with this. Someone asked me about what my velocity dispersions mean, and I said, well, we could plot this against bulge mass. We have these beautiful HST images for all of the megamaser disk galaxies now, and Ronald Lasker at MPIA is working hard to do the bulge disk decomposition. So I should hopefully have that figure for you. Okay, so for the last part of my talk now, I want to get back to this question of space densities. Back to these really small black holes that live in galaxies that are LMC-like and smaller. So I tried to look at this for my thesis, but as I told you, when you select samples optically, you have this horrible problem that you're biased towards the most luminous, optically luminous galaxies. Goulding and Alexander and collaborators used a mid-infrared selection, and they were basically down to estimated black hole masses of 10 to the 6th, not really finding any change in the AGN fraction as a function of black hole mass. So that was about as far as they could get in a uniformly selected mid-infrared sample. So I had to write this review, and I wanted to say something about the occupation fraction in lower mass galaxies. These optical selections weren't going to work, so what you really want is something like an X-ray sample with a uniform mass distribution, so you have your comparisons at high mass. And lucky for me, someone had done this work. This is what Ellen Nagallo and Tommaso and Brendan Miller have been doing with their AMUSE survey. So they've pointed Chandra at a bunch of early type galaxies where you don't have to worry about star formation contaminating your X-ray measurements, and they're measuring X-ray AGN fractions as a function of stellar mass for a uniformly selected sample. So I just did this very boneheaded thing and assume that the distribution of Eddington ratios is the same for galaxies of all black hole mass, all stellar mass, and then take the active fraction at high mass down to some fixed Eddington limit and compare that to the active fraction for galaxies below 10 to the 10, and I derive something like an occupation fraction of 50%. And then I tried to compare with Marta's models to try and say something about seed formation mechanisms. She and I still need to figure out what I did for the x-axis, but that's okay. But the main problem here, of course, is that I made this assumption that the Eddington ratio distribution is independent of the mass scale. That turns out to not be true. So now Brendan Miller and Elena have been just doing a beautiful job taking the entire AMUSE sample and trying to quantify actually the occupation fraction, allowing, they've parameterized the Eddington ratio distribution as Lx over m star, so they're allowing that to be a free parameter, fitting for that and the occupation fraction at the same time. So this is just the parameterization of the occupation fraction, so going to 0 at stellar masses of 10 to the 7, and then in some smooth way going to 1 by stellar masses of 10 to the 10. And you see we're not really getting strong constraints, but the preferred value is around 70%. This is really hot off the press. We just got this newest draft yesterday.
This is a fraction of active black
No.
or total?
No, this is occupation. So you allow both yes or no, there's a black hole as a free parameter, and the Eddington ratio as a free parameter. Which?
And what's the difference between the large number of blue spots and the small
Sorry.
number of spots?
So the red is the data, and the blue is one of his realizations as a model, just to show you how he's populating these models.
Sorry, on the contour one, what's on the x-axis, or the y-axis?
This is occupation fraction.
But the parentheses.
Percent for m star less than 10 to the 10.
Okay.
So really the only part of parameter space that we're ruling out is less than 20%. That's strongly ruled out. But 100% is not at all ruled out. And 70% is the preferred value.
What is LX and for
So that's this.
defined?
this is what else is getting marginalized over. And the intrinsic scatter also, because the amount of scatter, yeah. So that's where we are, and Brendan's doing a lot of work thinking about ways we could tighten these constraints. And in the paper, he says things like, well, if we had an X-ray PSF of 0.05 arc seconds, we could do a lot better. So it's going to be hard work, but I'm really glad we tried. So this is where we are. This is where we are today. Okay, so that's pretty much everything I wanted to say about little black holes and small galaxies. We know that there are black holes in bulgeless and dwarf galaxies, both red and blue, including at least one star-bursting dwarf. We still don't know what the occupation fraction is, although we're working hard to figure it out. I think we have to give up on our being wedded to these optical searches and really try as much as possible to have multi-wavelength searches in the future. And that's all I'm going to say for this part of the talk. I want to say a little bit about feedback, but are there more questions here before I go on?
When you say that you think the black hole mass does relate to bulge, despite that broad scatter under the relation?
What I'm trying to say is I think that some physical mechanism involved in making bulges is also important in growing big black holes, whether it's merging or whether it's actually accretion and feedback. If you're in a galaxy that hasn't made a big bulge, like the megamaser galaxies, then you can have a black hole, but you're probably not going to fall in the M-sigma relation.
So it's a two-path story?
Yes. So by bulge is important, I mean making the bulge is important in establishing a scaling relation.
Right, but you can also get there by a different path.
That's right. And it looks like you'll be less efficient at growing your black hole, so you'll have a much wider range of black hole masses.
So, can you come back to the black hole mass losses, server velocity plot?
Sure.
That's the first time that I see it. So,
We just got the referee's report.
okay. Okay, so here, can you say a bit more about what the various points?
Yeah, so, well, you can see what our sample is here. So the red points are the ones that Ailey measured herself from the VLA data.
They're very well constructed.
Right, and so you see that mostly they were megamasers, but actually we had a couple other dynamical black hole masses in our sample. The other thing she did was just a massive literature search. So everything is now done at least consistently. Okay, all right. So then we just wanted to show that these are the spirals and these are the S0s and ellipticals. So these are just the handful of ellipticals that happen to have H1 disks. And then all she did was say, okay, I'm only going to use exactly the same sample with sigmas, and these are all these measurements are taken from McConnell. So we didn't do anything to those measurements. So just so we could compare apples to apples.
So just a very basic question. But the circular velocity that you put in the plot is what? Is the line width? Is the peak of the rotation curve?
So we went around and around and around about this. Okay, so what Ferraresi did was take the outermost point that happened to be measured. What Cormandy did was take the peak. What Ailey did was define an error bar that was big enough. I mean, basically, that's what she did. I mean, there are only a few that are really, really lumpy, and those just have big error bars. The things that we threw out were things where we were not getting beyond the optical radius of the galaxy. And if we kept those, the scatter went way up. So we decided that was observational problems, and we threw those out in the end. 5 of them or something.
What scales? The optical radius, what kind of scales are you talking
A D25, so, a few kiloparsecs, 10 kiloparsecs. So all the measurements in the final plot go well beyond that. Otherwise, if you're inside that, you don't know. So that's what we did. She worked incredibly hard to try to believe that our intrinsic scatter is really intrinsic scatter, but again, I think we're really fundamentally limited by dynamic range here. So we have to do something better to get the big black holes. It is just, I think basically what we have to do is dynamical modeling to get halo masses here, which at least we can then compare to halo masses here. And they're both model dependent, but at least, you know.
What we know about all these galaxies is very strongly dependent on what kind of data they have for what galaxies. There's a lot of inhomogeneity in these kind of black mass models.
You mean from the sample selection point of view?
Yeah, like what you're applying.
Well, these are all spirals. I mean, because they
Right,
need to have
the
H1.
data are all the same, right? And all the black hole masses are measured in the same way. Not all the circular velocities are measured.
The circular velocities are really pretty consistent. That was
All
the
the
work that
main
she
ones?
did. Yeah. There's a few optical, but the optical ones are the ones that don't go out very far. So those are the ones she ended up tossing.
Right.
So that part, I think, is about as uniform as you could hope for at this point. But as you say, the black hole masses are certainly measured different ways. We're going to be stuck with that for a very long time, I suspect. How am I doing on time?
Total 15 minutes.
Okay. So should I talk a little bit about feedback? So this is work that Nadia Zakomska and Gulin Liu have been doing. And I want to show it because it's cool. I'm not going to go into all the interpretation. I just really want to show the observations, which are really neat. Okay, so the motivation for this is that, of course, people realize that the binding energy in black holes is so large that if you just tap a percent of it, you can solve a whole host of galaxy formation problems. You can get rid of big blue, massive blue galaxies at low redshift. And so we were very motivated to find evidence for this black hole feedback. And of course, globally, it's sensible. We know that black holes grow when galaxies grow, and we know that there are these scaling relations between black holes and bulges today. But in detail, when we go and try and look for evidence that the actively accreting black holes are also doing major damage to their host galaxies, it's very hard to pin that on the black hole. And the reasons are, first of all, because we know that star formation exerts feedback on galaxies. We know that very well. And so to convince ourselves in any given case that it's the black hole and not star formation, turns out, is really hard. It's also hard because it's a scale-dependent problem. So Daniel and Mike make very compelling case that there are accretion disk winds, and they're clearly exerting feedback on scales that matter for the black hole growth. But what we're interested in is galaxy-wide scales, kiloparsec scales. And there it becomes much more difficult. It's also a hard problem because it's a multi-phase problem. We see neutral outflows, we see molecular outflows, which perhaps carry most of the mass. A lot of my observations are of these ionized gas outflows, which carry no mass, but we hope are a tracer of something interesting. And then, of course, there's projection effects. So the classic work on this was from Stockton and McKenty, 1987. And they did a narrowband imaging survey of all the known quasars at redshift of 0.5. And they only found very extended emission line regions in the radio loud sources. About a third of the radio loud sources showed these 50 kiloparsec scale extended emission line regions. And so since then, people basically have said, okay, feedback is exerted by powerful radio jets. That's the end of the story. And, that's very sensible because radio jets entrain warm gas and carry it out of the galaxy. But very small fraction of AGN have big radio jets. So if we want to understand whether black holes exert feedback, we'd like to look at systems that are not radio loud. And that was the goal of my project with Nadia. So Nadia has the perfect sample, which she picked out of Sloan for her thesis. These are obscured quasars, so we don't have to worry about accretion light. We can see the host galaxy directly, but they're about the most luminous quasars that money can buy at redshift of about 0.5, and this is based on the O3 luminosity. So we have this perfect sample where the black hole is very strong, but we can still see the galaxy directly. And Nadia's done lots of follow-up observations, HST with Chandra, with Spitzer. So we started with long slit, spatially resolved observations. I'm not really going to talk about those today. And then we got to the real good stuff, which is the integral field observation. And this is what work that Gu-Lin Liu has been leading. He's Nadia's postdoc, and he'll be on the job market. So please pay attention to him. And the first kind of crazy thing, so we've now taken the 11 most luminous sources that we could observe with Gemini from Nadia's thesis, redshift of 0.5 to 0.7. And this is now just the flux in the oxygen 3 line. This is a 10 kiloparsec scale. These are all on the same physical scale. So these are obscured quasars with completely round ionized gas nebulae. Every single one is just completely round, and they're all 10 to 20 kiloparsecs in extent. So considerably larger than the half-light radius of the galaxy. So that's puzzle number one. When you look at radio loud sources, they're much more flattened, typically along the radio jet, although not always. These are type 2s. We might expect to see ionization cones. We don't. We see very round ionized nebulae. Crazy thing number 2, I saw this with my long slit data, but it was long slit data, so nobody believed it. The line widths are very broad across the entire face of these nebulae. So out at 10, 20 kiloparsecs, we see 800 kilometer per second oxygen 3 lines, and they're broad everywhere. Okay.
Question, do you think
Yeah.
Is the sharp edge is something an artifact of the way you presented it?
The here,
Yeah.
it's just dropping off pretty smoothly.
Okay, so there's some background, and that's where you.
That's right. That's right. So we've just cut off the noise. There's nothing magical about that.
The obscuration here comes from the black hole, right? Some kind of torus is obscuring, or is it?
Well, for a few objects, there's polarization measurements, so there's certainly obscuring material near the black hole. But I think that the fact that these are round tells us that it's probably patchy. And probably most of the gas at large radius sees the ionizing source, although we do not see the ionizing source.
But there are few elongated, right? Yellow on the top.
This little guy?
Yeah.
Yeah, that's definitely the smallest one. It's also got really wonky kinematics. So this is this W80 that Nadia's measured, and this shows the line profiles, which are high and drop only very slowly as you go towards large radius. So you can look at the paper, which is actually now accepted, et al. 2013. And Nadia puts forward a model where we're basically seeing a spherical outflow, and these line widths are basically then just velocities. In that case, and if you imagine that you're basically entraining all of this gas that you see at large radius, you infer very large kinetic luminosities of a few percent of the bolometric luminosity of the AGN. I'm not 100% sure this is a unique way to interpret the observations, but it certainly suggests very powerful feedback in these sources. So that's pretty well all I have, except I'll show you my favorite source, which is this ionized gas outflow that we found in one of the type 2 quasars. So these are the two continuum sources. This guy gets a lot of press because it might also be a dual AGN, but I like it because of this perfectly round expanding bubble, which if you just pretend it's a supernova remnant, gives you something like 10 to the 44 to 10 to the 46 in kinetic energy coming out. And so we try in the paper to argue that although it's a ULERG and clearly must be star forming, that likely it would be pretty hard to drive this outflow from star formation, partially because it's highly polarized and partially because there's just, you need 1,000 solar masses per year in star formation, which we just don't see. And so we've got, well, we don't know. If we just take all of the ULERG luminosity and pretend it's all star formation, we don't get enough star formation. If you can, there's one little place where if you take my lower limit and the energetics and the upper limit, but it seems more consistent that the black hole is doing something. This is Julie's picture now in the X-ray in pink. And in HST, you can see the H alpha which is very clumpy, tracing the outflow. And this is our ALMA data, which ILA is reducing now. So we'll know where the molecular gas outflow is shortly as well. All right, I'll stop there. Thank you. Mike.
Can you tell us a little more about the type 2 quasars that you were just talking about? How do these are?
So I think bolometric luminosities of 10 to the 45 to 10 to the 47 is what we estimate from the O3.
Okay. And your spectra cover the O3 H beta region?
The IFU, that's it, just the H beta O3 region, yes. The Sloan spectrum is a little broader than that, obviously.
And do the O3 to H beta ratios match?
So
photoionization?
they are very interesting. It would take me a long time to find. I can show you. Julian, I think, knows a lot about this. I think he's talked to Nadia about it quite a lot. But they are totally pegged at 10 to 15 and flat, a ratio O3 to H beta of something like 10 to 15. And they stay flat. And then at some magic break radius, which is pretty similar for all of them, they start to slowly decline, which Nadia interprets as going into a regime where you're running out of gas to ionize. And she actually uses that to figure out the energetics of the outflows in the second paper. But it's pretty compelling to think that the AGN is photoionizing the entire galaxy.
Yeah. Just a minor point. How do you get oxygen 30 kiloparsecs away from the galaxy?
What do you mean? There's gas there.
But there's having intergalactic gas is fine. Having metal-enriched gas that far away is interesting.
No, that's very common.
You're not that
I'm not sure it's that interesting.
metal-enriched spirals are pretty strong, and you get very low abundances and very long radii. And in order to get the classical O3 to H beta ratio that high, you need fairly roughly solar abundances. You can't have wildly low metal.
I don't know.
Where O3 is O3 is the dominant cooling.
I don't think we can say a lot about the metallicity.
And at low densities, O3 is also the major cooling.
I don't think we can say a lot about the metallicities. And I'm not sure that 20, 30 kiloparsecs is quite far enough away to be. I mean, these. Okay. We say that the typical size is 15 kiloparsecs of the.
Trying to read the bottom axis.
This is 10. Yeah.
So it is 15 kiloparsecs.
Yeah. It goes out to 20.
Yeah, the only thing I'd add is that the photoionization analysis remains puzzling enough that I think there's still some loose ends, and amongst them are, given the high speeds, there could be interesting shocks in this outflow, which would produce local UV. So
right.
Some of the photoionization would be local and not necessarily straight from the AGN.
And that is the other way that Nadia is pursuing to get the roundness. So instead of basically direct photons seeing all the gas, you could have shocks. And she says it works. I haven't seen it yet, and I just wonder if there's enough photons from shocks.
The shocks are pretty efficient at these speeds, but I think there's still a lot of loose ends in the details. I haven't talked to her about it for maybe a month or so. Could well change her mind.
Yes, right.
But wouldn't the ionization parameters say something about that? So if he has more than O3 images, we could possibly...
She has worked extremely hard. So the helium actually goes up at this break radius, suggesting that indeed we're entering a matter-bounded regime. So that part sort of checks out. We don't have...
Can you elaborate on that statement? What does that mean? So say that
I'm not going to remember exactly how this works.
Helium what?
Oh, helium-2. Helium-2. So basically, the density is dropping. We're running out of things to ionize. And I think it was Julian's suggestion that the helium to H beta should actually go up if the reason that the O3 to H beta drops is because we're entering this matter-bounded regime.
Actually, I think that was someone else.
Oh, okay.
Right. I think someone else had the idea.
This is what we see. We don't have incredibly high signal to noise in the IFU data for lines other than O3 and H beta, and we don't have a very wide wavelength coverage in the IFU data.
Well, but you have H beta, so you can presumably count number of recombinations and see
Yes.
if you get enough ionizing from the nucleus.
I think that's easy. It's like few 10 to the 8 to few 10 to the 9 solar masses of gas that's ionized. And I don't think there's any problem. I mean, we have a lot of photons to work with.
We got that about liners.
But you don't have the Aurora 4363 or 33 line, right?
No, I mean,
It was in the spectrum.
it's certainly in the Sloan spectrum.
Because from that you can see the excitation from the...
I think the problem is sensitivity too. We would have to bin probably the whole IFU. I mean, we spread out the light a lot to get these.
Yeah, it's too weak.
Carmen, what line was this?
The third of
The 4363 to try and
43, 63, or 68?
63 to see if it's consistent with shocks. So something is stirring up the gas because 800 kilometers per second is not virialized, but I don't think we know exactly how that's working. Thank you.